Good morning. Myself, Mr. Dibyendu Mondal, Assistant Professor of Greater Kolkata College of Engineering and Management under GIS Group. Today, I am going to discuss about solid mechanics. This is my lecture number 3 of Module 4 and today's topic numerical problem on compound cylinder. Finally, this video is uploaded in YouTube. Let's start. Okay. A compound cylinder is made by shrinking a cylinder of external diameter 300 mm and internal diameter of 250 mm over another cylinder of external diameter given 250 mm and internal diameter 200 mm. The radial pressure at the junction after shrinking is 8 Newton per millimeter square. Find the final stresses set up across the section when the compound cylinder is subjected to an internal fluid pressure of 84.5 Newton per millimeter square. Here, for outer cylinder, external diameter that is equal to 300 millimeter. External radius that is equal to 300 divided by 2, so that is equal to 150 millimeter. Internal diameter 250 millimeter and radius at the junction that is equal to 250 by 2, that is 125 millimeter. So for inner cylinder, internal diameter equal to 200 millimeter. Internal radius that is equal to R1 200 by 2, so that is equal to 100 millimeter. Radial pressure due to shrinking at the junction that is equal to 8 Newton per millimeter square. Now, fluid pressure in the compound cylinder P equal to 84.5 Newton per millimeter square. Stress due to shrinking in the outer and inner cylinder before the fluid pressure is admitted. Lamb's equation for outer cylinders are Px equal to B1 by x square minus A1 and sigma x that is equal to B1 by x square plus A1. So at x equal to 150 millimeter and Px equal to 0, substituting these values in equation 0 equal to B1 by 150 square minus A1, B1 by 22500 minus A1. So at x equal to R star that is equal to 125 millimeter, Px equal to P star that is equal to 8 Newton per millimeter square. So substituting these values in the equation we get 8 is equal to B1 by 125 square minus A1. After calculating you get B1 is equal to 8 is equal to B1 by 15625 minus A1. So subtracting the equation 3 from equation 4 we get 8 equal to minus B1 by 22500 plus B1 by 15625. That is equal to minus 15625 plus 22500 divided by 22500 into 15625 into B1. Therefore, B1 is equal to 8 into 22500 into 15625 divided by minus 15625 plus 22500. That is equal to 409090.9. So substituting the value of B1 in equation we get 0 equal to 409090.9 divided by 22500 minus A1. Therefore A1 is equal to 409090.9 divided by 22500. 18.18. Substituting the values sig A1 and B1 in equation we get sigma x equal to 409090.9 divided by x square plus 18.18. The above equation gives the hoop stress in the outer cylinder due to shrinking. The hoop stress at the outer and inner surface of the outer cylinder is obtained by substituting x equal to 150 mm and x equal to 125 mm respectively in the above equation. So sigma 150 equal to 409090.9 divided by 150 square plus 18.18. So after calculating, that is equal to 36.36 Newton per millimeter square. So Lehm's equation for the cylinder are Px equal to b square by x square minus a2 and sigma x, that is equal to b2 by x square plus a2. So at x equal to r1 equal to 100 millimeter, so Px equal to 0, there is no fluid under pressure. Substituting these values in equation, we get 0 equal to b2 by 100 square minus a2. So equal to b2 by 10000 minus a2. At x equal to r star, that is equal to 125 millimeter, Px equal to P star, that is equal to 8 Newton per millimeter square. Substituting these values, 8 is equal to B2 by 125 square minus A2. So B2 by 15625 minus A2. Now, subtracting the equation from this, 8 equal to B2 divided by 15625 minus B2 by 10,000. So B2 by 10,000. So B2, if you take common, 10,000 minus 15625. So 15625 into 10,000. So after calculation, we get minus 5625 B2 divided by 15625 into 10,000. Therefore, B2 equal to, after calculating, we get minus 222.2. Substituting the value of B2 in equation 7, we get 0 equal to minus 222.2 divided by 10,000 minus A2. So A2 equal to minus 22.22. Substituting the values of A2 and B2 in equation, we get sigma x, that is equal to 222.222.2 minus 22.22. Hence, the hoop stress for the inner cylinder is obtained by substituting x equal to 125 millimeter. So sigma 125 equal to minus 222.2 divided by 125 square minus 22.22 minus 14.22 minus 22.22 36.22 Newton per millimeter square. Compressive. Sigma 100, that is equal to 222.2 divided by 100 square minus 22.22. So that is equal to minus 22.22 minus 0.22.22, so minus 44.44. Stress due to fluid pressure alone. When the fluid under pressure is admitted inside the compound cylinder, the two cylinders together will be considered as one single unit. The hoop stresses are calculated by Lehm's equation, which are Px equal to b by x square minus a, sigma x b by x square plus a, where a and b are constants. So at x equal to 100 millimeter, Px equal to P equal to 84.5 Newton per millimeter square. Substituting the values in equation, we get 84.5 equal to B by 100 square minus A. So equal to B by 10,000 minus A. At x equal to 150 and Px equal to 0, substituting this value in the equation, 0 equal to B by 150 square minus A equal to B by 22500 minus A. Subtracting equation 12, we get 84.5 equal to B by 10,000 minus B by 22500. So B by 22500 minus 10,000 divided by 10,000 into 22500. So that is equal to 12500 into B, 10,000 into 22,500. So capital B equal to 84.5 into 10,000 into 22,500 divided by 12500 equal 1521000. Now substituting this value in equation, 0 equal to 1521000 divided by 22500 minus A. Therefore A equal to 1521000 divided by 22500 equal to 67.6. So substituting the values of A and B in equation, we get sigma x, that is equal to 1521000 by x square plus 67.6. Hence, the hoop stresses due to internal fluid pressure alone are given by sigma 100 equal to 1521000 by 100 square plus 67.6, that is equal to 219.7 Newton per millimeter square. Sigma 1521000 divided by 125 square plus 67.6. So that is equal to 97.344 plus 67.6. 164.94 Newton per millimeter square. So sigma 150, so that is equal to 1521000 by 150 square plus 67.6. So the answer will be 135.2 Newton per millimeter square. The resultant stresses will be the algebraic sum of the initial stresses due to shrinking and those due to internal fluid pressure. Inner cylinder that is equal to F100 that is equal to sigma 100 due to shrinkage plus sigma 100 due to internal fluid pressure. So minus 44.44 to 219.7. After calculating we get 175.26 Newton per millimeter square tensile. F125 that is equal to sigma 125 due to shrinkage plus sigma 125 due to internal fluid pressure. So that is equal to minus 36.22 plus 164.94. So that is equal to 128.72 Newton per millimeter square. Outer cylinder F125 equal to sigma 125 plus due to shrinkage. Sigma 125 due to internal fluid pressure. So 44.36 plus 164.94 equal to 209.3 Newton per millimeter square tensile. So So F150, that is equal to sigma 150 due to shrinkage plus sigma 150 due to internal fluid pressure. So after calculating we get 36.36 plus 135.2, that is equal to 171.56 Newton per millimeter square, that is tensile. Actually, initial difference in radii at the junction of the compound cylinder for shrinkage. By shrinking the outer cylinder over the inner cylinder, some compressive stresses are produced in the inner cylinder. In order to shrink the outer cylinder over the inner cylinder, the inner diameter of the outer cylinder should be slightly less than the outer diameter of the inner cylinder. Now, the outer cylinder is heated and inner cylinder is inserted into it. After cooling, the outer cylinder shrinks over the inner cylinder. Thus, inner cylinder is put into compression and outer cylinder is put into tension. After shrinking, the outer radius of inner cylinder decreases, whereas the inner radius of the outer cylinder increases from the initial values. R2 is equal to outer radius of the outer cylinder and R1 is equal to inner radius of the inner cylinder. So R star, that is the radius of junction after shrinking, or it is common radius after shrinking. Radial pressure at the junction after shrinking. Before shrinking, the outer radius of the inner cylinder is slightly more than R star. Inner radius of the outer cylinder is slightly less than R star. Now, for the outer and inner cylinder, Lamb's equation are used. These equation are Px equal to B by x square minus A and sigma x, that is equal to B by x square plus A. The values of the constant A and B will be different for each cylinder. Let the constant for inner cylinder be A2, B2 and for outer cylinder A1, B1. So at the junction x equal to R star and Px equal to P star, hence radial pressure at the junction P star equal to B1 by R square minus A1 equal to B2 by R star square minus A2, or B1 minus B2 divided by R star square equal to A1 minus A2. So B1 minus B2 equal to R star square A1 minus A2. Now, the hoop strain or circumferential strain in the cylinders at any point, sigma x by E minus Px by Me. But circumferential strain, increase in circumference divided by original circumference, 2 pi r plus dr minus 2 pi r divided by 2 pi r, dr by dr, that is the radial strain. Okay. On shrinking at the junction, there is extension in the inner radius of the outer cylinder and compression in the outer radius of the inner cylinder. At the junction where x equal to R star, increase in the inner radius of the outer cylinder, R star sigma x by E plus Px by Me. But the outer cylinder at the junction we have sigma x equal to B1 by R star square plus A1, Px equal to B1 by R star square minus A1. So A1 and B1 are constant for outer cylinder. So increase in the inner radius of the outer cylinder R star 1 by E sigma x plus Px by M. Okay. Similarly, decrease in the outer radius of the inner cylinder equation minus R star sigma x by E plus Px by Me. Okay. So, decrease in the outer radius of the inner cylinder is equal to this one. Okay. So, okay. Okay, thank you. uh, so my lecture video is uploaded in YouTube. If you like it, you have to subscribe my channel, and if you face any problem, you may contact anytime through mail or over telephone. Okay, thank you.